geometry of the surface. And there are two directions of isocurves as well as two directions of principal curvature lines. So there's one, there's another, and they make these grids. This grid is not necessarily quad panelizable. These are not necessarily flat. Those are definitely flat. Okay. Sometimes the principal curvature lines are the isocurves, like on the torus, they're the same. And sometimes one of them is the same and the other one isn't. And that is the case on the hyperboloid of revolution. One of the isocurves is straight, the other is a circle. Principal curvature, one of the principal curvatures is a circle, the other is the curve that is shown there. Okay, so if you're using the principal curvature, you cannot use the isocurve method and necessarily be sure that it'll be flat. Okay, then there is this idea. This is from the previous module. This idea of the panelization methods you learned previously, and this idea of quad panels. And really, the difference is that those work on whatever curvature network whatever network of curves you put on the surface. And this only works on a specific type of curve network, which is the principal curvature network. And then there's this idea of quad panels versus developable strips. And that is simply the idea that in the limit, in one direction or in the other direction, quad panels become developable strips. That's what we're doing. Then there is this idea of developable strips versus developable surfaces. So I've seen some of your models, and sometimes people feel like they need to discretize something that looks like that. And you don't. You can just unroll it as is because it's already developed. The only reason you would need to discretize it is because you can't unroll it all into one sheet, or it like overlaps itself, or it's too big to fit on the piece of paper, which is common in architecture. So that's why I'm making you make models slightly bigger, so we have to break them into parts anyway. But you don't have to discretize it. That's different. Okay. And then so that's the methods you learned in the previous class, the methods you learned in this class, which are quad panelization, and the difference between making something into developable strips and making it as a developable surface. Some of you would have the gooey surfaces that you need to stripify. Others of you have smooth surfaces that you only need to break where you need to break them in order to actually cut them and put them together. Okay, then you all know this idea of in 2D, what a normal and a tangent is. And then in 3D, we talked about it. There's a normal and a tangent plane that is the plane that contains two tangents. And those tangents are tangent to the isocurve, and the normal is perpendicular to the plane. The theme, though, that I want you to understand is this idea. This is an important idea. This is an analytical method of finding the tangent. Many of you asked the first class, how do you find the tangent? So this is the analytical method. This is the calculus method. You have a parametric equation for the curve, and you differentiate it, and you get a parametric equation for the tangent line. And computers always do this. You just take smaller and smaller and smaller and smaller and smaller and smaller increments until you just find it. And they don't have to be that small. So anytime you want to do anything computationally, it's always done like this. From fluid dynamic simulations to finding a tangent line, it's always just tiny, tiny increments. The same is true for this idea of curvature. Basically taking 3 points along a curve, bringing them closer and closer together, and they converge to generate a circle. Or you could do it the analytic way. So this is computation, that's analytic. And then this idea of curvature is really just the radius, 1 divided by the radius. So it's the inverse of the radius. So if something has a small radius, it's curving slowly. If something it's curving quickly. If something has a big radius, and a line has a radius of infinity, and it has a curvature of 0. And so sometimes when you're trying to do the principal curvature script on a surface that's already developable, it will not work because it's trying to find something with an infinite curvature. Okay. So this is the other important idea. I feel like this idea, we've talked a lot about developable surfaces, but I have a simpler way of talking about it, which I think is helpful. And I just want to do it for a second to make sure everybody understands. There are curvy surfaces and there are twisty surfaces, and they are different. Basically, these are twisty, and this is curvy. If it's curvy, it means that in one direction it's straight. I can put a plane on it, and it will lie on a line perfectly, like that. There's always a line that's contained in a plane. That's what it means to be developable, that there's a plane that lies on it, on a line. So it's basically the sweep of a series of planes like this. Whereas if you look at these, the plane only touches on a point. Okay, so that is the difference. That is literally what it means. This is positive curvature. This is negative curvature. The plane cannot be smushed in there. But here I can do it like that. So if it's a twisty surface, I have to have a twisty material to smush it on it. If it's a developable surface, I can roll a plane around it. Yes.
Technical terms?
Twisty and curvy?
Yeah.
No, it would be developable, and it would be Gaussian, you know, what the curvature is. The curvature would be zero Gaussian curvature, or it would be isometric to the plane. All of those words are just mean twisty versus curvy. And for some reason, materials don't mind curving. I have no idea why, they just don't. And they do mind twisting. So your materials will break if they twist, and they will not break if they curve. So that's I just, you know, I keep making all these scripts with the developable loft and everything like that, and all it's trying to do is figure out how to put a plane between things. So it's funny because when the technical terms are, you know, very hard to understand, but actually differential geometry is quite intuitive, and it comes down to that, basically, and looking at tiny small bits. Okay, and so then that is what it means for the Gaussian curvature. Okay, so Gaussian curvature of 0 means that it is just curvy or flat. It's either a plane or flat, and Gaussian curvature of greater or less than 0 means that it's twisty. You can't unroll it. Mean curvature is different. It just means how curvy is it. So both of these are curvy. That one's twisty. This one's curvy. Both of them are curvy. And then the minimum radius, which is or the minimum maximum curvature, this one is variable because it's a cone, and this one is constant. Okay, so those are the ways, the characteristics of a surface. And this is what I was just talking about. The technical term for a developable surface is that it is the envelope of a family of planes. And I find that completely confusing to explain to people other than like that. Okay. Okay. And so then this is the difference when you smash something versus when you unroll. When you smash it or when you unroll something that can't be smashed, the area is not the same. That's area is the same when it's unrolled. When you smash it, its area is much smaller. So it's not the right shape. So we have two problems. There's two problems when you want to build something. The first is the problem of unroll. How do you get something that will not roll, that will not flatten, is not isometric to the plane, or is twisty into something flat? And then the second problem is re-rolling. Once you have the right shape in plan, can you roll it back up around the surface? That's the other problem. Okay? So there's always two problems. The first is, can you unroll it? The second is, can you re-roll it? I gave you 3 methods for that. Okay? and they are these. Triangulation, the developable loft, and the principal curvature panelization. So when you triangulate something, it always unrolls to the correct area. But re-rolling depends on the material because it might still be twisty. When you use this developable loft, sometimes it doesn't work, but re-rolling would always work. And it would work with some curves. When you use the principal curvature, it always unrolls, re-rolling always works, but it requires a specific set of curves in order to work, which are the principal curvature line. So that's like this. Triangulation is just taking the developable loft is looking for the least twisty moments and giving you a guideline for how you might lie a plane. Like if you imagine a curve here. And a curve there. It's trying to search for the best place to lie a plane across those curves in space. And giving you a guide for which areas to loft together. And then the principal curvature is a completely different shape that is always going to work, but requires these particular curves. So triangulation solves the unrolling problem. It always unrolls to the correct shape. But it doesn't solve the re-rolling problem because it's still twisty when you try to re-roll it. The developable loft works some of the time, but you get these sort of weird divisions as it tries to find where there might be developable surfaces in here. You know, looking for where the least twisty moments are. And then the principal curvature uses the same method from before, which is the computational as opposed to the analytical method of migrating itself along the surface, looking for the places to draw a line. So those are 3 methods. And then if we were to put the methods from module 1 into this, they would be like this in this terms of characterization. They always unroll to the correct area. Re-rolling always works. They take any input curves, but they deviate from the original form. Whereas all of these are a close representation of the original. Okay, so that's sort of like a categorization of the methods. Okay, then in terms of, then we went into talking about joinery and how to join things. And what I feel like I would like you to know from the grasshopper thing as a basic starting point is just these things. So what is a vector? Vector is direction with an x component, a y component, and a z component. What is a plane? A plane has an origin and a normal and a y-axis and a z-axis. Then this idea of what is a parameter. A parameter is the location, the sort of address of a point along a curve. And if you reparameterize, you get 0 to 1. And a UV coordinate, what is a UV coordinate? Is the similar thing. It is the address within a surface. So this is 0.5 because it's traveling along the middle here, and then this address is changing. So, and this basically is the evaluate curve component that lets you evaluate a point along a curve, and that is the evaluate surface component that lets you evaluate a point along a surface. And that is how you find things on a surface. And I wanted to, before I keep going with that, I wanted to say one other thing, which is about these things. What panelization really is this. If I shine this light on this, it's producing a curve right here. Okay? And also the rays of light are perpendicular to that curve. like that. And if I can find a place where these rays of light that are perpendicular to the curve pass through another curve, then that will be flat. So on well-behaved surfaces, they pass through twice, produce a flat thing, which is sort of like the penumbra, which is the fuzzy zone in the light. In fact, people often write algorithms that are actually based on shadow in order to panelize things. Okay, so then there's how to get the normals on a surface. This is something that the other thing I feel you need to know, and it's a very, 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 very simple script. It takes a bunch of points, a poly surface in a VREP, uses this closest point thing to put the points on the surface, and gives me the normal and the points that I can draw a line and extend that line. So you can always do this, even if you can't find the points in any other way than marking them manually. You can use this little bit of code just to put points in here, a surface in here, and it will draw the normals for you like this. And then you can extend them in two directions like this, and that will allow you to make bolts. And how to get the tangent planes is just this. This is all it is. It is the same bit of code, the points, the closest surface component, and then instead of drawing a line, making a plane with the origin and the normal, which produces all these planes down here. And many of you asked last time how you would copy something around on the surface, how you would orient things to a surface. It's with those planes. But essentially, these two components are all you need to find the locations and construct the orientation to any poly surface that you would put in. I feel like if you know those particular things, that is sufficient for you to do most of the things that you would need to do for making a model. But also you will meet with me with your specific problems, hopefully you will, and we will design little scripts for you around things that you together. That's the only way to do it, okay? All right. Then in terms of model making techniques, these are the ones. How to create an overlap, how to create a weave, how to create bolts, how to create a zipper, how to create a stitch, how to create an egg crate, and how to create a slot. I haven't gone through these yet. I'm going to show this again. Some of you asked me about this the other day, but I'm going to do it again. I'm going to show you some of these things again. Not all of them, not going to go through the zipper again. But okay, so, and I want to show you how to troubleshoot the principal curvature, because some of you have run into issues with it when it comes up. I've met with some of you, but that's what I'm going to do. Okay, so this is, I wanted to show because sometimes when you have a surface like this, you can't offset it. You can't just very easily make an offset. If I try to offset this by a lot, it will eventually get strange. It'll not be very like the surface anymore, okay? So sometimes, I mean, that's ridiculous, I'm just exaggerating, but sometimes I will manually create an offset, and even though it is not following the surface, it is not a direct offset, it works better. So for example, here, I took the normals to this surface at each of its sides, like that. And then I offset a curve over here. So it's like this. And then over here, I produced I just moved the curve by the same amount. And then what I wanted to do is to make sure that these would stack on top of each other. So what I can do is rotate this. By the way, I won't know that you would know this, but it took me some time to figure out, but I looked at various ways of constructing an offset, and this is what I figured out sort of works for a conoid. To rotate these 5. And then to loft and produce your own version of the surface over there. Why did I move this down? I moved it down because I wanted it to line up in height with where that one is, so that this becomes a straight line still. And the reason for that is, so this one actually has to be taller than this one, because I wanted this horizontal to still be straight. So the reason for that is that I'm trying to produce, I don't know if you guys remember, I'm trying to produce this thing where they stack. So I want horizontal plane in there. So in order to do that, I needed to sort of construct my own offset where this line is remained horizontal. Okay, and then when I have several layers here, what I did is I did the principal curvature on each one, which is sort of annoying, but took an isocurve like this, extended this surface. Opened up my grasshopper. I've also collected many of the scripts for you now, including the ones that I put on the that I showed today. Use my principal curvature. There's 2 in here. This one takes curve. This one takes points. Okay, so when you're doing this, there's always 3 steps. The first one is input some original curve, like this, into here. Put the surface in there and get a bunch of curves that are going to be my divisions. So I'm going to get some in this way. I'm not going to use that one. I might move this down so I can get the spacing that I want. Okay, and then bake those. And then I need the other direction so that I can get it very finely and quad panelize it. So I'm going to take one of these and I'm going to put that in here. I'm going to switch the direction, crank this up a lot, and get a bunch of curves. Sometimes part of the surface isn't filled, and then I need to take a new curve and fill that in. Okay, so I'll bake that, and then I'll put those on their own layer. Now, if I'm doing an overlap, I'm not going to use this first one. I need another set of curves because I want this one. I don't want a bunch of panels next to each other. I want this one to go under that one to go under that one, and that one to go under that. So what I'm going to do is mark all these points along the edge. Move those over a little bit. Put those in Um, so then this one here, it takes points, put the surface in there. With this, and then I'm going to get a second set of curves that are offset slightly from the original. Bake those. And I'll take those and put those on their own layer. Now, there's always one other step, which is rather annoying, but it's that these curves, you can see, they're not quite hitting. They're not quite aligned, the curves in one direction with the curves in the other. So if I try to put a panel in here, it's gonna be sort of messed up. So what I need to do also is always mark the ends of these curves with points, which I can do by selecting them, going curve end. It's long thing. So curve start. That gives me those points. I can take those points, put those in here. And then that gives me some additional curves that I need to add. So I can go over there, take those. And then once I have all of those, I can take those, add them to this list. And I can take this whole group of stuff, copy it over. And then here, I can take all these curves and split them with this line and that line. Okay, so once they're split, sometimes some of you have told me it won't split. And when it doesn't split, so all of these split. Oh no, good, some of them didn't. Okay, so these, when they don't split, you can trim using this line here. And that's just like a kind of a loose, bad approximation. The reason it's not working is just because it's because of the tolerance here. The step size is not totally on the surface. It's moving along the surface in a series. Okay, so you can do this trim thing, or you can do this, use this little script down here, which is called loose intersection. And that takes a bunch of curves and you put them in there, and it takes another curve in here. And that gives you the points on curve A where they sort of intersect. You can bake those, and then you can split the curves with the points. That will always work. Okay, once these are made, you can go through here and you can select them all, rebuild them with 2 points, and then lock them together with straight sections. And then you can go in and tag the end with a little triangle. And that will work and unroll. Okay. Now, what I end up doing is, in order to do the overlap, is I end up hiding this first surface, taking all these points, putting those in the point script, taking the surface that's behind it, and using that surface. And then it will find the closest lines on that surface that are to those original points. I will bake those. I'll find the other direction and I'll do the whole thing again. And that will give me strips like this that are on a series of surfaces that are offset. So that in order to do that, I basically go down the line. I produce a series of offset surfaces doing the same method again and again and again and again and again, and then I check to see whether they will stack if I wish. And then I go through them one by one, doing the next row on the offset surface. Okay. All right. So that is the overlap. Some of you I know have situations where you are doing something like on a shape like this. This shape doesn't require the principal curvature, but when you think about how it's going to make a global shape when it comes together, when you're overlapping things, it's still a challenge that you need to sort of think about and get your head around. So some of you I know are doing weaving things with linear strips rather than the principal curvature strips. I'll get to that in a second. But just want to show you what can happen here, which is if I were to extrude, if I were to take the tangent here from this intersection point. Actually, I think I'm just going to loft. If I loft between, well, I can't do that because, okay. You can't loft between two principal curvature lines unless they are trimmed by the other two principal curvature lines. So like a loft from there to there will not be developable. It will be if it is split by those like that. So I can loft there, and I can get a surface, and then I think I can probably just array this surface all the way around. Okay, so something like that, but if they're going to overlap, which is what I'm talking about right now, if I extend these by a little bit, and then I do that, right, I get something like that where they're intersecting. And so if I were to try to account for the thickness, I could take all of these, I could put them in an order using the script that I provided that goes the tools, Rhino script, load. You can load the ordering script. These, because I created them through an array, they should already be in an order. But if I put those in Grasshopper, I made this little thing called offset series. It's very short, takes a poly list, it calculates the length, figures out how much to offset, and offsets them all in a row by increasing amounts. So if I put all these in, if they are in an order, and then I bake this, you'll see that by the time it gets around offsetting, I extended these too much, so the overlap is too much. The thickness is built up. Let me show you the one I made previously. So I made one, by the way, with a full torus, and the reason for that is it's easier, I think, to trim the strips than to construct each strip individually. And then I array them around like this. So let me use these, which construct the full thing. If I put those in here, this is offsetting each one in a row by this amount. So there's 0.1. The thickness eventually builds up. And you get a like a gap, which I have to say I think is fascinating and beautiful and wonderful. The idea of thickness, like, and it's the thing that I want you to encounter. I mean, you could easily just offset every other one in and out, in and out, in and out, in and out. But the direction of, if you keep offsetting a series, one on top of the next, on top of the next, on top of the next, they will progressively get further and further away from each other, which is potentially amazing and beautiful, or potentially annoying, depending on what your goal is. So the way I did that here is I had all these strips, I put them on layers, and I just went tool, Rhino script, run, used my reorder script, went around in a row, selected all of these in the order that I want them to offset. And then I put them in here. And then I hit bake. And they are, you can see there's the starting one and it's going around increasing the offset. Now I know they're still sort of overlapping, and that's because I maybe didn't offset them enough, or maybe I did. I feel like that's a material thing. How much more they would need to be offset is something you'd have to test in a material. But either way, I think as you move into the next stage, starting to think about how thickness is going to build up, or just letting it happen and letting it fail. Okay, so that's that trajectory. Then I wanted to talk a little bit about the weaving again. So if you are doing the weaving, okay, the weaving requires two versions of the surface overlapping each other, one with one direction and one with the other direction of curvature. So in this example, like what I always do is again get the principal curvature lines in both directions, and then choose some that are going to be the major in one direction and some that are going to be the minor. Choose some in the other direction that are going to be the major and some that are going to be the minor. Then I split these into parts and lock them together. And then these strips, theoretically, they would be able to weave through each other. However, it's very much a material issue that would come up if you try to take this one over that one and under the next one. And so what I tend to do is make them skinnier for bits of time. So tend to take one of the major sets of curves. The other major set of curves. Split this with that. Split those with these. And then essentially I can take every other one of these. Spike those with whatever diameter I feel I need to weave one through the other. With a diameter, I'm gonna guess because I don't know how big this model is. With a round cap. And I think I did this differently than I've done it. Sorry, I think what I've done actually is, but it might work either way, is to do them always in rows. With that, and then you can split that with these to narrow, to create gaps in the surface to allow the weaving to go through. Now, the issue with this is that when you unroll this, this is a funny shape. So I know some of you have been trying weaving with straight shapes. In order to do that, I feel like it will be necessary to have an armature. I've talked to others of you about armatures. And so an armature might be a 3D print. And you might do something like this, where you would take a strip, put it on the surface, extract a nicer curve from the strip. Divide that isocurve into, I don't know, 8 points. Select those points. Use the very simplest conceivable bolt script. Putting those points in there. Putting the surface in there. And then essentially baking those piping them and attaching those to the 3D printed armature and punching them as holes in the string. And then you could lay something on and then eventually remove the 3D printed armature. Alternatively, some of you are searching for other ways to make armatures that are easier, less expensive, or bigger. And what you can do for that is you can make egg crates. Okay, so the way you make an egg crate is very simple. You can contour an object in one direction. Contour it in the other direction. Make two sets of planar surfaces. Overlap those. And then you just need to create slots. So you need to make slots that go halfway up one and halfway down the other so they can fit together. It doesn't need to be this dense. And so the way to do that, pretty straightforward. I put up something that does that. Basically, what it does is okay, so this takes one set of surfaces in one direction, another set of surfaces in the other, intersects them, and then splits out the split intersections into two groups. So if you bake those, it gives you half the intersection like that and half the intersection like that. By the way, I've often done this manually. You would have many less height threads than I have here. And sometimes it's confusing which thing is supposed to go on top. So I don't think it's a problem to do this manually. Essentially, what you do is you intersect. I could, by the way, in this particular case, literally just split them in half with a plane down the middle. And then what I always do to intersect two surfaces rather than building the thickness is I pipe them with the thickness of the material as the diameter. So half of the thickness of the material as the radius. And then I split the top half out of one set of surfaces. And then separating them, and that ends up like this. So like half two sets, and if you were to take two of these and look at them, Um, um, so if you offset these by the same thickness in both directions, if you made the diameter, so they'll be able to slot through each other. Like that. So when I want to make a very like cheap, affordable armature, what I will do is make it out of a few cross sections of chipboard or plexiglass, something like that, in that manner. And then I might add nubbins on them to stick through the surface, so I have something to pop onto it. And that also can come apart, because if you have more than one or two cross sections through each other, it won't need to be glued, and so you can build something on it and then just knock it apart basically, and take it out, as long as it's not completely self-contained within there. Okay, this only works if the things are 90 degrees to one another. If they're not at 90 degrees to one another, if the planes are at some other weird angle in space, like that, passing through each other bizarrely, the radius that you pipe the middle needs to be bigger, and that radius is so I rarely model thickness of things. I simply, when they intersect and I want to knock one out of the other, I just pipe it. There actually is I've actually done this rather complicatedly and figured out that it's this. You can calculate the angle of incidence and figure out how big the pipe should be, but it's not really necessary. Like, you can just guess how big it should be and make it larger. Okay. Then the other thing is I did want to show you the interlocking process, and then I think I'll probably be out of time. So this is the model here that Shelley made. It has this sort of feathering connection where two surfaces overlap. There's three bolts that overlap, and so for that, I made this very manually, but I'll go through the bolt thing again as I'm doing it. I essentially had a situation like this. And this is a developable surface. So going back to what I said at the beginning, there is no reason this needs to be subdivided at all. However, if you unroll it, it'll overlap itself. And also, it was too big for the sheet of wood and aluminum that I had, which is a very common problem. So I just looked at this top surface and chose lines that I wanted to divide it down into. Just visually facing these lines. And then I also spaced both. So the red lines here are going to take the bolts, and the purple lines are going to take the are going to be split. However, in order to figure out where, like, let's say I want to know where this offset from this line hits this surface. What I do to do that is simply draw a normal to the surface. Extrude the curve along the curve. And intersect that with the other surface. So what it took me a while to decide where I wanted to put these lines, but I was going back and forth and seeing where they would land on each surface by putting them on one, projecting them to the other, putting them on the other, projecting them back to this surface. And then, if you remember, I'm not sure all of you remember. In here, Shelley tried this before, and we tried it, and it didn't hold together because there was only one bolt at the seam, and it was coming apart. So what I found is the only way to get things to hold their curvature across a seam is to have at least 3 points of connection. And I stole that from a friend of mine, Nick Rushia, or I was inspired by him. He's doing something different. His are overlapped in a different way, and they run cross contour with each other. But I did see that he needed this long joint in order to make the wood curvature work. So that is what you need if you want curvature to hold across the joint. Is multiple points of connection across the joint. And so in order to create this long tooth, what I did is okay, I took the inner edge and the outer edge like that, joined them, and then I tweened them to create a bunch of curves. Then I selected all of those, rebuilt those with less points, so they're smoother. With a degree 3. And then fold them back to the surface. One. Then once I had this, I took every other one. So every other one is going to have bolts. And then I took every other one that was going to be for a tongue. Gave them their own layer. And then I decided, since this is the bolt hole, that I need a little bit more distance on either side. And then I split this, all these curves with each other to draw the thing, which is probably confusing, but it'll be less confusing in a second. Something like that. And then, oh, I kind of screwed this up, whatever. Okay, and then joined all of these. And because this is routed, I needed to put a radius on the corners, which is difficult because these are 3D curves, so they won't fillet. I can't just fillet them, probably. And so in order to do it, what I did is, Rhino often can't fillet, but it can find a radius in this manner. If you give yourself a guide curve, and then you do a circle tangent. And the reason it can do this is because it's possible to fit a circle planimetrically there, but it's not able to calculate where the circle would need to go to fit a particular radius. So I can make my own little radiuses down the corners. I curve, and then I can split them with this curve like this.
Are they necessary to round the corners, or is this just an aesthetic thing?
Well, it's necessary if you want the pieces to fit together because the router can't make a point. So the router will go here and then turn, and something will happen there that is hard to predict. Like if you're using the Zun cutter, if you're using the Zun with a knife, it can make a sharp corner, but the router, it has thickness, so it will go and it'll be rounded, and then it'll, if you want the two surfaces to hug each other, you need to put the roundedness in yourself. And then also you need to add tolerance. So what I ended up doing is, after I made this, I piped it with like a millimeter of thickness, and split it out of both surfaces. Okay. And then I manually marked all these points like that. Went into my grasshopper, opened up the bolts simplest thing here, and put the points in here, put the B rep in here, and very long, making bolts and extending them, and then that'll also tell me where they're going to hit the other surface. So I can go over here, like take those, and then pipe those with the radius of my bolts. Okay. All right. So then the only other things that I feel, I went through how to create a a zipper and how to create a stitch, but you have those in video. The other thing that I feel is sort of essential is this idea, just the two kind of basic structural ideas that I was talking about. And one of them is just the difference between compression and bending. You're going to take structures next semester, but next year actually, but basically structural forces resist things different ways, and so bending is when the curvature is being bent, and that is what is resisting the deformation. And interestingly, torsion is the other force that is resisting the twisting that I talked about at the start of this class, right? So this is resisting curviness, and this is resisting twistiness. And materials resist each of these forces differently based on their internal composition. Okay, and then the only other idea I wanted you to be familiar with is this idea of elastic deformation versus plastic deformation. So some of the models that I was making had a plastic deformation where the metal is just flexy and sprung together only by the joint. And some of them have a plastic deformation where in the middle, the metal is actually folded. And I went through how if you want to fold the metal in plastically so it holds its shape, you need to do it around a break. You need to do it around a point. So you need to put the metal, like basically if you have a vise, you can put the metal in, you can put a break in the vise, put the metal in between two pieces of wood that come to a point and fold it over. Or they have a break in the metal shop, but you have to have a point where the metal will not fold precisely. So that is the other idea that I went through. Okay, so that I believe covers, I think, basically like other than, I feel like coming out of this class, what I'd really like you to have is what we're going to go through now together with as a group, which is how do you bring your what we're going to go through together individually, you with me in your groups, which is how you bring your digital models closer to represent your ambitions in reality. And then the other thing is a sense of how this works. So you understand what types of surfaces can be built and why the different methods of building them might or might not fail. Some sense of the difference between computational methods of finding things in little bits and analytical methods of calculating them. And also a model that you're okay. There's one other thing that I wanted to say before I end the class, which is I think so I know everyone in the world and a lot of people in this country have been really bummed out. I went to the MFA on over the weekend, and there were more people than I've ever seen in my life in the MFA. It was utterly mobbed, and apparently they were completely not expecting this. The MFA was just totally filled with, it was so diverse too, so many different types of people. There was no sort of crowd that could be identified. And I found out this is true across the country. I found out it's true in DC, and museums have been mobbed. Why is that? It's because people look to art when they want to find hope, okay? And that is what you are all engaged in, is in the darkness of your stress and exhaustion, making things that are inspiring to others, okay? So, and also ultimately will be inspiring to you, whether or not you like them right now. So have faith, and that's, it will turn out all right.